right, good afternoon, everyone. I hope you have a good lunch break. My name is Tzu Hao Chow. I'm representing Broadcom from the Optical Systems Division. Just a quick background for what we do. We are in the business of data communications. So we serve optical devices and CPOs to interconnect networks in the AI networks and also in the data centers. So let me jump into where optical interconnects are today. So optical interconnects generally can be found from the front-end networks and the AI scale-out networks. So these are served by optical pluggables, for example, transceivers such as the DR4 or FR4-based transceivers to interconnect across servers and via the switches. And also, more recently, with the AI infrastructure coming out, AI scale-out has been already dominated by transceivers such as the SR8s and energy SR8s or 800G FR4 single-mode optics going up to 1.6T. So these two segments are very well served by optical interconnects. What today we are looking, or the industry has a lot of focus, is the scale-up network. Scale-up network traditionally has been dominated by copper links. They need very high reliability, extremely high bandwidth connecting GPU to GPU. This may be served by NVLink switches running copper. So for example, maybe 8. Bandwidth requirements is almost 10x or even more compared to scale-out or front-end networks. Very high density. So how is it that as we move to higher data rates and bigger cluster sizes, this is a bottleneck that we may need to actually overcome with optical interconnects, and probably even starting like yesterday. So what actually drives towards adopting optical interconnect technologies in AI scale-up networks? So today, with 100 gig per lane, interconnects. With copper, the reach is up to 4 meters with a power about 4 to 5 picojoules per bit. If we go to 200 G per lane, this reach can be, it will drop down to 2 meters. And power-wise, doesn't save much. This actually limits the connectivity to within one rack. You want to grow bigger cluster sizes, that's going to be extremely challenging. So this is an example of a NVL72 rack, considering the amount of cabling, copper cabling on the backplane. So as we move to a higher data rate, this challenge of routing copper in the backplane is going to be challenging, especially with liquid cooling and power considerations. With 100T switches, generally we are looking at liquid cooling. You need to bring pipes and power delivery, higher power per rack. So that really poses a lot of challenge with copper link. So how can optics overcome this? Do it by disaggregation. So this is an example of still maintaining a single node scale-up domain, supporting beyond 144. And the size is actually only limited by the radix of the Ethernet switches or the switches up in that layer. So where does the optical components lie in each of the area is you have the one inside the XPU, so bringing out the high bandwidth in the fiber shuffle up on top with the patch panel and fiber jumpers, and also inside the switch to connect, supporting this high cluster size. For optics to actually be deployed in such a disaggregation networks, it needs actually to be very power and cost competitive compared to copper. So we are not comparing between optical technologies, but actually we are actually comparing against copper. How do we bridge the gap to be get optics adopted in the AI scale-up networks to replace copper? So where is actually the line where we want to look into AI scale-up networks with optics? So that line that we draw here, we make an estimate that today with copper links, the power density or the power efficiency is about 10 picojoules per bit. So with AECs, ACCs, or DACs going down, practically it's just the SerDes power. Traditional CPO today, or by next year, is getting very close to the line, but it's still not bridging that 10 picojoule per bit. What we do see that in the not too distant future, by 2028, we have the intermediate CPO and advanced CPO by 2029 that can bridge the gap to get down to equivalent of what we see today with copper links. So this is one metric around power with the CPO technology. Now, however, I just want to point out that with VCSEL NPO, which I can cover a little later, the power efficiency can get down to 5 picojoules per bit total, including the SerDes power. Now, this is only just the power element of the system. This is not the benchmark. It's a critical benchmark, but not the only benchmark. So other benchmark that we need to understand or need to consider comparing against copper is escape bandwidth. With copper links today, we can see that it's limited to about 12.8 terabits per second. This is basically limited by the beachfront of XPU or GPU. With optics, with oceanfront and beachfront, that we can place very dense optics, we can support up to 50 terabits per second. Power-wise, we can get down to 10 picojoules per bit, so it will be comparable. Importantly is cluster size, which is a function of reach as well. As we get more need for additional computation power and more tokens, we will need to have to increase the cluster size. So optics can support up to 1K. So running up to 30 to 500 meters, we can bring it across the entire row or across maybe multiple rows with optics. But with copper, you are limited to within a 3-meter reach and probably only about 144 cluster size. Cost is definitely a big consideration. Today, copper links are less than 10 cents per gigabits per second. We believe that with advanced CPO and with VCSEL NPOs, we can get down to the 10 cents per gigabit per second range. Interop and technology maturity is also key consideration, especially so with reliability. Server vendors and users have been very comfortable in scale-up links running copper. They are extremely reliable. We need to bridge the gap from the optics standpoint to actually convince and have the confidence that optics don't fail in such scale-up networks. So I'm going to propose a couple of scale-up solutions. The first is an MPO concept, and next will be a silicon photonics-based CPO concept. So let me start off with some MPO technology comparisons or considerations. So earlier, Charles did mention about micro-LED. It is one consideration for MPO technologies using for scale-up. So comparing VCSELs and silicon photonics as well. So if we look at the VCSEL technology, the energy density can get down to 1 picojoule per bit. Pretty similar to what micro-LED can do, but in the case of optical communications, micro-LED probably do need a reverse gearbox that will potentially bring up the power in support with the high-speed SerDes. Silicon photonics today, with an LPO-based solution, that's running about in the ballpark of 5 picojoules per bit. So in terms of comparison, just by the VCSEL itself, because of the low energy, low bias current needed, you can really drive it down to 1 picojoule per bit. For cost, as mentioned earlier, with the VCSEL-based solution, we can really approach 1x of what copper can do today. Fuel reliability, having less than 0.1 feet, is based on actually fuel shipment data that both from our side and from our peers that we can get sub 0.1 feet. We have shipped trillions of our device hours without any fuel returns based on the laser itself. Another key parameter for performance is the prefect BR. So as of maybe a couple of years ago, LPO with VCSEL-based solution is still fairly, I would say, weak compared to silicon photonics. But today, I think with the VCSEL-based LPO solution, we can really achieve around E-10 BER performance, very similar to the silicon photonics-based solution. I just want to point out for fiber count, in the 3.2T engine MPO concept, the fiber count here is reasonably controlled at the 64 because we are running 100 gig per lane of bandwidth. So the number of fiber count is considerably less. Compared to micro LED, where running with a big array, you definitely need way more fibers. So fiber handling on that front will be a challenge with the micro LED technologies. Moving beyond 100 gig, VCSEL technology for the next generation in scale-up networks can be scalable. So either going faster with higher data rate VCSELs, pushing to 200 gig, or with wavelength multiplexing technologies. Silicon photonics has already proven that they can run at 200 gig per lane. So that is that has a pathway towards 200 gig. On micro LED, at this point, is TBD at the moment. So the takeaway message here is, right, we believe that VCSEL NPO does provide the best energy efficiency and cost for scale-up links. A summary of what I mentioned earlier, how we achieve the 1 picojoule per bit is with local power CMOS driver and TIA. LPO today running with silicon germanium based technologies can already achieve maybe, say, in the ballpark of 3 picojoules per bit. So pushing it further down is with the 1 picojoule with CMOS. I mentioned about reliability earlier, that we have field data with ourselves and our peers that pushing the device service hours to 5 trillion device hours with no field returns. So that actually gives the confidence that the VCSEL devices are reliable to be used in the scale-up network. Here is a concept of how this VCSEL-based MPO can be implemented in a server, a GPU server. So over here, showing here with engine that is a 3.2T, placing 2 of them in the beachfront of the GPU substrate will support 6.4T. So this is to scale. Meaning that one device here is about maybe 20 mm by 20 mm. So having 2 side by side already supports 6.4. If we need additional bandwidth, we can definitely place more rows to support the escape bandwidth, which with 30 meters OM3 fiber, which is at a very cost-effective position, is more than sufficient for covering multiple cluster sizes. I mentioned earlier with 1 picojoule per bit power consumption with the advanced CMOS driver and TIA. So this technology today is mature. We have module vendors that have been supporting multi-mode transceivers that they have been shipping in very high volume. It's highly scalable. We have the prototypes, the devices with the arrays that we can start actually prototyping this very quickly. So that is on the VCSEL NPO concept with a low energy efficiency and 1 picojoule per bit. I will move on to the silicon photonics-based CPO. So this is another approach that we can look into how optics can work in the scale-up domain. So power-wise, today, probably a little bit higher, but we are trading this off with a longer reach. Up to 2 kilometers reach with DR-based or FR4-based solutions. I would like to point out that in terms of scale and the bandwidth density, silicon photonics does have its advantage of supporting up to 51.2T of short line density. And in fact, if you want to push it further, this will definitely be able to support 2 terabits per second per mm. How do we get to 51.2T? We make use of this concept of the ocean front, where this typical XPU or GPU has a width of about 50 mm, and placing 4 optical engines across it will get us to the 51.2T. Compared to traditional pluggables, this is a 10x density improvement in the bandwidth. So a key concern with CPO technologies or with any optical technologies is reliability. And Broadcom has been in the area of CPO for a while, and we do get a lot of feedback from our peers and from our end users of, how is this, how reliable is CPO? So here are some tests, reliability tests, qualification tests that we have done. Here shows the temperature cycle, unbiased damp heat, mechanical shock and vibe, and dust. So in particular, I want to point out that for mechanical shock and vibe is a critical thing, and also on dust, because this is a new technology, how a CPO device can work as well compared to traditional switch network. Is based on all this qualification data, and our results are currently showing that all the units are passing. We have run through many systems, and I believe our peers in the CPO technologies there will also be having similar data that we need to prove to the industry that this device is reliable. Optical connector is another area that it is new. So I mentioned earlier about the dust, how we can manage dust in a CPO environment. Traditional ODMs, they are familiar with installing switches in the boxes. It's all electrical. They don't need to care about dust. And running devices out from the switch, that area needs to be something that really needs seriously considered. So in this case, we are showing that with our switch devices, how we can control or mitigate the dust issue is with the connector and with a dust protection device. So running through all this qualification data is showing a good performance in terms of the insertion losses, especially like, for example, I mentioned mechanical shock and vibe and dust, that we are all passing it. So this connector is showing that it is reliable with, on the hardware side. So on this, the other key thing earlier I mentioned that relating to the hardware reliability. This is more on link stability. It's just as important compared to hardware reliability. Because today AI networks require links to be extremely stable to enable long computational runs, either for training or for inference. So in our own internal test, we run this over 1,200 hours, so over almost in the ballpark of about 2 months. So we do not observe any link flaps. The reason is we do believe that statistics in the CPO, noise statistics in CPO generally follows the Gaussian distribution, meaning that the FAC engines can actually correct for all these random noises, allowing that and correcting it so that it will run error-free. Presence of DSP and also with different insertion loss in, for example, a switch does actually impact or introduce burst errors, so which the FAC engines have an issue correcting. So we do have feedback from end users that, hey, with transceivers, they do see link flaps pretty often. And this is an area where I think link stability of CPO will benefit the overall runtime of massive AI clusters. This is a notable development that if proven right will drive the CPO's rapid adoption. Okay, in summary, for optical networks, optics, front-end and scale-out networks will be continue to go towards higher data rates, 100G, 200G, and 400G with pluggables and CPO. We do see that there will still be a lot of use cases there. So from the Broadcom side, we do also support the pluggables with our component devices. And for CPO, we do believe that this is with the lowest power solutions for single mode links, and this enable the movement with this deployment in the switch area, we can move out into scale-up interconnects. And for scale-up interconnects, we need to provide cross-rack interconnects with large cluster. Oh, there's a typo here, disaggregating. Pardon me here. So cost, reliability, and escape bandwidth are important consideration I mentioned. So we need to be competitive with copper solutions. MPO, so VCSEL-based and CPO technologies will see a lot more deployment use cases. And lastly, I mentioned earlier that the CPO reliability of both the hardware and link stability will be key. Currently, link stability is showing good promises. And we will need to have further deployment and in the field to actually prove out this point. And that will really drive the rapid adoption of CPO technologies. And okay, thank you. With that, that concludes my presentation.
Now it's open for discussion. Anyone want to ask questions?
Hi, very great talk. Can you have more discussion on how you reach 1.6T by having those VCSEL?
Oh, okay. So actually
looks like an array.
Yes. Yeah. So the engine that was shown there is actually a 3.2T. So today we already have a 1x4 array VCSEL. So going to higher data rates, we will have to stack more arrays. But obviously, to get a good balance between performance and use and so on, we will have higher array density that we are looking into.
Please, thank you.
For taking my question. So my question is about your EML, your external module laser, right? So I think you have a very high market share in that domain, right? But it seems like there is another camp want to develop like a constant wave kind of laser to commoditize the market, right? So I read some article last year when you share here, you think EML still competitive in the short term. 1 year after, do you change your view? Thank you.
Okay, good question here. So for EMLs, right, I think as we see with every generation of data increase, so let's say from 100G, or maybe I start from 50G to 100G to 200G, EMLs generally will always take the lead because this is a proven technology for mass market adoption, good reliability, good performance. So this is where generally the market or the module vendors will start adopting technologies to push it to that higher data rates. Now, we do understand that the silicon photonics is also coming up. So like you mentioned, with CW lasers supporting silicon photonics. So that is an area that will definitely have a role to play, and not a small role even. So the technologies will coexist. But with any new technology adoption first, I think, again, EMLs is the push. We still see that the EMLs have a long tail, or not long tail, that have always the first entry to the market with a proven reliability. I think that is really the key that drives the market adoption or the acceptance of EML technologies.
I have one question. If opticals can be used, I mean, while adapting scale-up networks, do you think it's still need to put more and more GPUs into a single rack?
Okay, so the advantage of having optics as an interconnect in AI networks is you can do disaggregation. So the advantage, you can optimize AI rack just with GPUs. Currently today, I think the general concept is you have the AI servers and the switch in one rack, or maybe across two racks and connect one another. But now if we consider disaggregation, you can simplify your rack design, both in power, cooling, and so on, because the requirements for a switch and a server may be different. And that is where I think we will need the optics to connect between the servers to the switch in a disaggregated form. So you split the two up, and then you can really optimize the design and simplify the design there.